tock, tick, tock, while kissing the person we love or being late for a meeting. Who has never dreamt of slowing time down? Well, as a physicist, I have great news for you. This is possible. But how? This is a phenomenon predicted by Einstein. To understand it, we can picture the universe as an immense tablecloth distorted by massive objects. Ourselves, the Earth, stars, galaxies. These distortions affect both space and time. Thus, a clock placed in such a distortion ticks more slowly than another one located in the middle of the cosmic emptiness. So here I am in Switzerland, the land of watches, writing a PhD thesis about a distortion of time. It is a very small effect, and yet a very real one. Without accounting for it, our GPS systems would be inaccurate. But what if time weren't distorted exactly as Einstein predicted? Maybe this could help us solve some of the greatest mysteries in the universe. Why do we observe galaxies moving away from us faster and faster when gravity is supposed to be attractive? Is this a sign that Einstein's brilliant theory of gravity has some flaws? To try to answer these questions, I studied the distortion of time on the largest possible scales, using galaxies located billions of light years away. Of course, we cannot send watches out there, but we can measure the distortion of time on these scales by observing its impact on light. Imagine light as a wave traveling through our distorted cosmic fabric. The light wave emitted by a galaxy located deep in its distortion will be stretched as it comes out, and it will change color. The more a wave is stretched, the redder the light becomes. Thus, by measuring the reddening of light, we are truly measuring the distortion of time. In my PhD thesis, I showed that thanks to new telescopes and satellites, we will be able to measure this tiny effect in the coming years, and use it to test the fundamental laws of gravity by comparing the measurements with Einstein's predictions. Time alone will reveal the consequences of all this. And in the meantime, after having written hundreds of pages of ink, words, and equations about time, I have learned to appreciate its elusive nature, always beyond the reach of even the most precise clock, when faced with the immensity of the cosmos.
In the vast silence of space, more than 15 billion miles from Earth, a small spacecraft continues its journey through the cosmos. Voyager 1, humanity's farthest traveled emissary. Launched in 1977 by NASA, Voyager 1 carried not just instruments and data recorders, but also a message, a golden record for any distant civilization that might find it. But perhaps its most iconic moment came not from its launch, but from a single photograph. At the urging of famed astronomer Carl Sagan, Voyager 1 turned its camera back towards Earth in 1990 and captured an image unlike any other. A tiny pale blue dot suspended in a sunbeam. That single pixel, our home, became a symbol of humility, unity, and the fragile beauty of life in the vastness of space. This image and Carl Sagan's speech that followed after inspired many to pursue careers in astronomy. Here's that speech, and today we talk to someone who was deeply inspired by it, Sveva Castello.
From this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
Hello, everyone, and welcome back to another episode of Space Bites with Benny. It's me, Benny, your favorite nerd. And this is another episode in the Cosmic Conversation series where we meet really cool people that are doing very cool things. And joining us today is Sveva Castello. Hi, Sveva. How are you doing today?
Hi, Benny. It's a pleasure to be here. I'm really excited.
Yes, I can tell. Do you want to introduce yourselves?
Yes, I can say a few words. So, my name is Sveva, and I am a cosmologist. I'm right now at the University of Geneva, where I've just completed my PhD on testing the fundamental components of the universe with the large-scale distribution of galaxies.
And what made you fall in love with cosmology in the first place?
So, cosmology is the study of the universe on its largest scales. And I think this is really fascinating as a subject because, well, first of all, it's a part of physics. And physics to me is like a form of philosophy of nature, a way of understanding really the deepest laws of nature, but with a scientific approach. And cosmology, in some sense, is the part of physics that touches the most fundamental questions about us as human beings, about us in the universe, and what are the fundamental properties of the universe. It's something that really I feel genuinely passionate about as a human being, I would say.
That's a very beautiful answer. To be honest, this is my favorite question to ask people when they come on the podcast because the answers that I get are always so like a couple of days ago I was doing an interview as well and the person said that they fell in love with cosmology when they went to this like space camp and they saw the Milky Way for the first time and it was like they were immediately drawn to that aspect of physics, you know? And this is very funny because actually a couple of days ago I watched the movie Oppenheimer and there's
Oh,
this
yeah.
one scene where he's in bed trying to fall asleep, but his mind keeps thinking about all these questions. And I don't know about you, but at least for me, I feel like I'm haunted by all of this knowledge because I feel like a responsibility to learn all of this stuff and to chase after it and really understand the universe. But in fact, the reason why I say haunted is because within your lifetime, there's only so much you can do. I don't know. Is this something?
I fully understand what you're saying. I mean, in reality, what I feel is that we know very little about our universe. We know, let's say, impressively much, considering all the progress we made and considering that we do have a standard cosmological model that can describe our data, that can give us some answers. But somehow, the more we look into the data and the more we learn about the universe, the more we understand how little we actually know. So I think it's a statement also about our finiteness as human beings and our in front of the vastity of the cosmos. So in some sense, you can either feel a sense of maybe some fear in front of what you don't know, or you can feel deeply fascinated about it. And this is personally how I feel about it. The idea of being able to use science to actually answer questions about the universe is something that is extremely fascinating to me. And and there is so much to learn still. And as you say, in a lifetime, we probably won't be able to answer all the questions. But we are part, of generations of scientists. So there will be more questions for the future as well.
Yeah, thank you for phrasing it that way. It's very beautiful. And what do you think of this idea that, of course, the atoms, the particles that make up our minds and make up our bodies are the same particles that make up the galaxies and the stars. So, what do you think about this? Like, I don't know how to say, but this sort of like relation between it is our body and our mind that is doing this research, and it's the same thing that makes up this thing that we are researching. So it's almost like it comes full cycle. So,
Of
what do you
course.
think about this idea?
Of course. I think I read a quote somewhere that says that we are the attempt of the universe to understand itself. And this is very true in some way because we are a part of it. So, indeed, I think if you look at it from, let's say, a more philosophical perspective, then indeed doing cosmology is really a way of understanding our place in the universe. And in this sense, since you asked me, what made me so fascinated about cosmology, let's say about astrophysics in general, then actually I would like to mention Carl Sagan, a very famous physicist, One, let's say, of the quotes and the speeches that I always carry with me is a speech by Carl Sagan, who was commenting an image that was taken by a space probe that took an image of the Earth from very far away. And it is, this little grain of dust suspended in the vastness of the cosmos.
I think this image is famous, right? It's called pale blue dots.
Exactly.
Yeah,
It's
okay,
pale
yeah.
blue dot. Exactly. And this pale blue dot speech by Carl Sagan is so beautiful. And it really states, that astronomy, astrophysics is the effort to understand our place in the universe. And it's a way of understanding what is around us and also understanding what is our place in it. And I think this speech is really a beautiful statement of how little and fragile we are, and yet how much we understand, and how fragile are, all our human issues like wars and the political issues in the face of this beautiful vastness of the cosmos. So indeed, astrophysics and cosmology remind us about our place in all of this. So I think it's really a statement about our humanity in the cosmos as well.
I agree. Honestly, yeah, I can talk about this all day, but then this episode will be 24 hours long and we cannot, unfortunately. Okay, so let's move on to the more academic aspect of
Yes.
cosmology. And tell me, what was your academic journey like to get to this point today where you just finished your PhD?
So actually, my journey started in Italy, where I am from. I'm from a small city in northern Italy, close to the Alps. And there I did my studies in high school, which actually were not really about cosmology. I actually had, in high school, I mostly focused on humanities. So I studied, a lot of Latin, ancient Greek, philosophy, history, literature, and I was really fascinated by all of this. I had a few classes in mathematics and physics, which were really good, but let's say the main focus of my program was on humanities. And so then towards the end of my studies, I started, asking myself the question of what I would study at university. And I was really passionate about philosophy, about, these fundamental questions that we've always asked ourselves. And in my spare time, I started, reading books about physics, about philosophy, about astronomy. And I realized that I was really fascinated by this idea of trying to answer these fundamental questions with a scientific approach, a little bit at the boundary between science and philosophy. And so I started getting interested in physics. And so in my spare time, I started studying a little bit about this. And when it came to picking, let's say, a study path for university, I decided to enroll into a bachelor in physics, which was a bit of a challenge at the beginning because I didn't have, really the same mathematical background as other people who had picked scientific subjects in high school. So the beginning was tough. But then, after a while, I managed to slowly get into the idea. And so I did my bachelor at the University of Turin in Italy. And during the third year of my bachelor, I decided to go on an exchange. So I went on Erasmus to Sweden, to the Uppsala University, a bit north of Stockholm. And during my Erasmus, I had to do my bachelor thesis. So I had to pick a subject for that. And so I started looking at the list of opportunities that there were and of research topics available. And I found this page about the astrophysics department, about the astronomy division at the Uppsala University. And I saw a description about, research on dark energy, gravity, cosmology, and this sounded really, really interesting. And so I decided to contact the department there to see whether there would be the possibility of doing a bachelor thesis during my exchange. And this is what happened. So I spent 6 months in Sweden. I took my first cosmology course there. And I got really, really passionate about it. And at the time, I decided, okay, this is what I want to do. This is really, for all the motivations that we discussed before, this is such an insightful field of research. I really want to spend time doing this. And so then I got my bachelor and I decided to stay in Sweden to continue with a master there in theoretical physics and astrophysics. And so I got my master's degree in this.
Do you think being in Sweden has some relation to you becoming passionate about cosmology, like specifically the country of Sweden?
Well, for sure, I would say that that was the place, as I was mentioning, where I had my first real, let's say, academic encounter with cosmology. So for sure, the fact of being there and having the chance of meeting researchers who really they were extremely welcoming. They really welcomed me and made me feel part of their group was really helpful in sort of pointing me towards this direction. And then at the same time during that period, it was, my first international experience. It was the first time when I was really exposed to studying in English, and I was really exposed to life as a researcher because I was spending time with this research group. And this is an opportunity that Uppsala offered me as a university. They were really open-minded. I think it was really the spirit of the academic community there. And then in terms of Sweden as a country, well, Sweden is not a densely populated country. So there are so many places where you can see, this beautiful sky. And this is so, so fascinating. I've seen the Northern Lights there quite a few times.
This is where my question came from, because I know that Sweden is very famous for this beautiful sky that it has. So
Yes.
I thought studying cosmology in a country where the sky is so beautiful must have been such a great advantage. Yeah.
Yes, for sure. Absolutely. We could see the Northern Lights sometimes in Uppsala, and this was really beautiful, but they were a bit faint. So if you really want to see some strong Northern Lights, you need to go a bit more up north. And I had the chance to do that through my partner who's Swedish. So we've been traveling a lot, and we had the chance of seeing this beautiful phenomenon. And actually, for the funny story, since you're asking me about this, when I was still a high school student, one of the ways in which I got even more interested in astrophysics and astronomy was to attend an astronomy camp organized by the European Southern Observatory. It was an astronomy camp that was intended for high school students, and it was a 1-week-long camp on the Alps at an observatory in the Aosta Valley. And to get into this camp, I had to produce a short video about my favorite astrophysical or astronomical phenomenon. And guess what? I picked the Northern Lights.
Of course.
And this was something like 3 years before I moved to Sweden. So it was, I think it was somehow written in the stars, if you want to put it that way.
I try my best not to be so cheesy, but to be honest, with a story like that, you cannot help it. It's beautiful.
Exactly. Yes, exactly. And yeah, it was then actually in this astronomy camp that I met my partner. So this was also a connection that I had to Sweden.
So you can say that you fell in love twice in Sweden, once with cosmology and once with your partner.
Exactly, if you want to say that. Even though we had been together before, I actually moved to Sweden.
Oh,
So
okay.
one of my reasons to go there was for
Yeah.
sure, the call of cosmology and also the call of love.
Of course.
Yes, but to continue the story, then I did my master's in Uppsala, which was, from an academic point of view, it was wonderful because the master program in Uppsala is a bit special. You can pick any course that you want within the master program in physics. So it was ideal for me because I've always been a bit in between, the more theoretical direction of theoretical physics and astrophysics. And so I could pick courses from both directions. So this was really nice. But this was during the pandemic. So it was a very special time. So I spent most of my master's actually studying from home. And, I have very positive memories of that time from an academic point of view. It was difficult from other points of view. But I still managed to, complete my studies. And I did my master thesis also in cosmology in collaboration with the Stockholm University. And then that's when I decided that I wanted to do a PhD in cosmology.
Mhm.
And when looking for, different possibilities, I then found the position that I currently have here in Geneva. It was a project that was advertised by a professor here in the Department of Theoretical Physics. And the description was really exciting. It was trying to understand the fundamental properties of gravity by observing galaxies. I mean,
So literally what you were looking for, like this is your calling.
exactly. I really felt the call for this. And so I applied and I got into the PhD program here. I got the position. And then I moved to Switzerland in 2021 in September. And I've been here since then, basically. And I've defended my thesis, let's see, slightly more than 2 weeks ago. So yeah, I still have to get used to the idea I can call myself a doctor now. And
Also, in fact, I should have introduced you as Dr. Sveva Castello, not just Sveva.
yes, so it seems, as I said, I still have to get used to it myself. But indeed, now I am a doctor of philosophy in cosmology, indeed. And so now I've spent these 4 years doing a PhD, which means writing a whole thesis, a very long document, doing research about a specific subject and really training to become a researcher, to learn how to formulate good research questions and slowly becoming more independent as a researcher. And this is where I stand.
So before we get into this topic of this very long document that you had to write up, what does an average day for a cosmologist look like? You know, you wake up in the morning, you come into the office, you know, or you just let's say before you go to stuff, you wake up in the morning, what do you do? How do you start looking at the sky and figuring out the universe and all the cheesy stuff that we said that in the beginning?
So one, let's say, the image that I had of someone working in cosmology when I was a high school student was someone who would sleep during the day, wake up in the evening, go to some remote location, maybe a beautiful telescope on top of the Alps, and then observe the whole night, collect data, and then in the morning analyze the data and then go to sleep. This was my image of it. I can say that it's not, let's say, too close to reality. This is maybe the image of what an astrophysicist could have done maybe a couple of centuries ago. But nowadays, cosmology, astrophysics are data-driven sciences that are very international. And so there is never, let's say, a single person making observations with their own personal telescope. We actually work with data from telescopes or from satellites that are based upon very large collaborations. So there are people who work much more in contact with the data, and maybe they work on the telescope side, usually very remote places like, the Atacama Desert or the Canary Islands, very nice. And then there are people who work on the data analysis and they are based at universities, and people who maybe work more on the theoretical side and trying to understand, how we can plan for future missions, what can we learn, what models should we test. And I belong a little bit to this last category. So my work is really based on, believe it or not, but pen and paper and chalk and blackboard. Actually, the listeners may not be able to see it, but while Benny and I speak, I have a beautiful blackboard behind me that is full of calculations.
It is in fact very beautiful. Yes, I mean I recognize some, how do you say, variables behind you. Yeah, it is very beautiful.
Exactly. So my work is really based on this, in the sense that I try to develop theoretical models and a theoretical understanding of how we can model, for example, the distribution of galaxies. So you can make pen and paper calculations. And then sometimes these calculations are numerical. So one can work, with a laptop or even with big computer clusters to make very complicated simulations or very complicated calculations. And then it's a very collaborative work. So during the week, I spend some time in my office making calculations, but then I have plenty of meetings with my supervisor, with my colleagues here. We are a big group here at the University of Geneva, and we discuss a lot with each other. And so I have several projects in parallel, and then for each project, we meet maybe once or twice a week. And I even have collaborators that are at other universities. So I've written, for example, a scientific paper with people in Canada, in Germany. So it's a very, international subject. So often, I meet with collaborators via Zoom. I have video calls. And then I travel a lot as well. It's a very international field. So we have plenty of conferences in various parts of the world. This is a very exciting side of the job. And so I get to travel to present my work at conferences, to discuss with colleagues. I've really been to Spain, to France, to Italy, to Sweden, to Norway, to Germany. I've been around in Switzerland, to the UK, to really many places during my PhD, to meet people, to discuss ideas, and to work together. And then a part of my work is also to teach. I'm part of the University of Geneva, so I teach in bachelor and master courses. I've also taught small courses in high schools. So this is really an important part of the job, to teach and to give back to the community what you do research on.
Do you enjoy teaching?
Yes, I really love it.
I can tell because you have such a nice way with words. So I was like, oh, I already know the answer to this question, but I'll ask anyways.
Yes, I really love it. I think it's a very important component of my job. Of course, it takes time. So sometimes, you have these busy weeks when you have 3 projects and you have to finish an important calculation. You have to finish writing a paper. This is what I didn't mention. I spend a lot of time writing as well. We write scientific papers, so that's an important component. Reading papers, writing papers. This requires a lot of focus, and sometimes, also have to prepare for a class on top of this. And it's not the easiest task, but it's really, I find it very rewarding to be in front of students and to exchange with them. I learn a lot from the students, and I've taught various courses, both mathematical courses for bachelor students, master courses. Usually, since until now I was a PhD student, I was not let's say the main lecturer for the course. I was in charge rather of the exercise classes, but I was trying to help students to solve exercises and to discuss with them. They could come to me if they had questions. And it was a really, really nice part of my job. And I also co-supervised a master thesis. This was also very enriching. And to, be able to share what you do and slowly be able also to, get on the other side. And I'm not much academically older than a master's student. I just have 4 years of experience more. But slowly but steadily, you feel that you're able to exchange and to mentor students. It's very, very nice.
That's very cool because, yeah, I think you can learn a lot from the people that you teach. And at least, to be honest, the way that you've described this PhD experience has only made me feel even more excited about graduating and, actually having the prospect of doing research full time. That's definitely very cool. Okay, so let's talk about this topic of yours, the one that you spent 4 years, researching. Tell me about it. First, what's the title? Like, how would you describe it in 2 or 3 words?
So the objective of my PhD is to test the fundamental properties of gravity and of the mysterious dark matter by looking at the distribution of galaxies. And in particular, I considered one specific effect that one can measure from the distribution of galaxies, which is the distortion of time.
Mhm.
So that's the idea. So you can tell me where you are to start.
I was waiting for some fireworks. When you said the distortion of time, I was waiting for some, music, background music, like the dun dun dun. Okay, let's start with what surprised you the most about what you discovered in this topic.
So first of all, already the idea that time can be distorted, if you think about it in a fundamental way, is really surprising. This is not something that I discovered. This is something that we know since a long time. It was Einstein who actually sort of put this into equations. This is based on the theory of general relativity.
Mhm.
That is our theory of gravity, that tells us that actually we can picture the universe as like an immense tablecloth that is distorted by the presence of massive objects. And so objects that have a mass create these deformations in space-time that we call gravitational potentials. And these are distortions in space, but also in time. So if you take a clock and you put it at the bottom of such a distortion, then the clock at the bottom will tick more slowly than a clock that is put outside the distortion. This is really fascinating. And it's a prediction of general relativity. It's very surprising. But what is really surprising that, let's say, of what I did during my PhD is that I demonstrated that this effect can be used to learn something about the fundamental properties of gravity and of dark matter by looking at galaxies. This is something that, if you had told me about this before my PhD, I would have been really surprised. Like, how on earth can we, first of all, measure the distortion of time from the distribution of galaxies? And how can we even use it to learn something about dark matter? This sounds really exotic.
And from so far away as well, because, these galaxies, it's not next door. It's not your neighbor. It's not your local co-op or something. It's, very far away. And something that whenever I think about, honestly, really sends me into this rabbit hole spiral is the number of galaxies that we know to exist.
Well, one thing is what we can observe is only a finite part of the universe. We can only observe up to a horizon. So, and this horizon is determined by the fact that, light has a finite speed. And so there will be galaxies that are so far away and that are receding from us because the universe is expanding in an accelerated way that their light will never have time to reach us. And this means that there is a horizon beyond which we can't really observe. So if you ask the question, how many galaxies there are in the universe, actually, the answer is that we don't know, because what we can observe is only a part of the universe. We can only observe the observable universe, which is defined, let's say, in size up to this horizon that we can observe.
And how can we test this? How can we test this?
You mean how many galaxies there are, or how?
No, this you're talking about this theory of gravity. How can we test this? How can we probe this parameter that you're talking about?
So first of all, maybe let me start about why we should do this. So why should we test gravity?
Yep.
Why? Because you can say, okay, gravity, we know how it works. I take an object, it falls down. This is gravity. But the problem is that if you go on very, very large scales, we don't really know whether the laws of gravity apply in the same way as they do on Earth. So
let me ask you before we continue very quickly, is it true the story of, because this is what they told us in high school, but is it true the story of when they went to the top of the Tower of Pisa and they dropped the, I think it was the cannonball and the feather and they saw, yeah, so is this true?
So this is an experiment that we think Galileo made, actually Galileo Galilei. And this is something that he was doing in order to understand whether all bodies experience gravity in the same way. And this is actually one of the fundamental pillars of our understanding of gravity. It's called the equivalence principle, which is the statement that all bodies experience gravity in the same way, regardless of their composition. And this is exactly one aspect that of gravity that we don't really know whether it holds or not, because we know that in the universe we have this dark matter. We don't really know what it is. We detect it in the sense that we see its gravitational impact on visible light, but dark matter doesn't emit light on its own. It's this, gravitational dark component that has an impact on the motion, for example, of stars in galaxies. We need it to explain these motions. We need it to explain the structure in our universe, but we don't know what it is. And so we don't know whether this dark matter obeys this equivalence principle and experiences gravity in the same way as standard matter. So this is one open question. Another open question is, do the laws of gravity really apply in the same way on very large scales as on Earth? Because as I mentioned before, the universe is expanding in an accelerated way. This is not really intuitive, because if gravity is attractive, then somehow the expansion should slow down. But we don't really see this. We see that it accelerates. And so how do we explain this? Maybe there is something that we don't really know and we don't really understand about gravity. This is why it's interesting to test gravity on large scales.
So now you explained why we should test it. And can you go on to explain how we can test it?
That's a very good question. There are many ways, actually. Many ways of doing it. Let's say if you look at very, very large scales, a natural way of doing it is to look at galaxies, the large scale distribution of galaxies. This is, let's say, the largest scales that we can access. And the idea is that if you look at how galaxies are disposed in the universe, their distribution will be sensitive to how gravity works. Because, well, galaxies will be formed from matter over densities, and then they will gravitationally interact with each other and with the underlying dark matter distribution. And so when you look at the galaxy distribution, you have to think that there is some underlying dark matter distribution that is like some form of scaffolding that we don't really observe directly. And then the visible matter that you see is sort of located in this scaffolding of dark matter. And so this will be sensitive to how gravity works on large scales. So we can use it to test gravity.
I like to say, when someone asks me what is dark matter or try to ask me to explain, I like to say that dark matter is like the invisible furniture in the room with which you keep bumping into because your leg hurts, but you cannot actually observe it. You don't see it, but you can feel it. We observe its effects even though we cannot directly observe it itself, and we don't know what it's made of.
Exactly. So we need it. We know that it should be there, but we don't detect it. We haven't detected it directly. People have tried doing it. Well, I'm in Geneva, so I can tell you about CERN. that is located here, people are trying to make these collisions among particles, very energetic particles, in order to see whether we can somehow detect some particles beyond the standard model of particle physics. But so far, we haven't really detected it. We just know that it should exist because otherwise, as I was saying, we can't really explain how structure forms in the universe. So it should be there. And so the idea of looking at this large-scale distribution of galaxies is really to see whether the galaxies are distributed as we expect them to be. So we can make some prediction for how the distribution should look like, for example, in general relativity, based upon Einstein's theory of gravity. And we can check whether this is consistent with observations or not. So this is one way of testing gravity through this. And so but in particular, what I did in my PhD is to try to understand then how we can use, let's say, not only just this large-scale distribution of galaxies, let's say in a standard way, as people have done so far, but we can also consider additional effects, so-called relativistic effects that we sort of have when we count how many galaxies we have. And one of these relativistic effects is indeed the distortion of time. And so the objective of my PhD was to try to understand how we can use the distortion of time that can be measured from the distribution of galaxies to test the properties of gravity and dark matter in new ways. So this is the objective of my research.
But it's almost like I'm waiting for the suspense. Like I know the answer, but I'm waiting for the moment that you say the title. You know what I'm saying? Like the main, like the thing, like how you're probing all of this.
So the idea is, well, if you want to hear about my PhD thesis title, that is A Matter of Time, Testing Gravity and Dark Matter with the Distortion of Time in Galaxy Surveys. So the idea is the following. So we can measure the distortion of time from galaxies because what we can measure is the impact of the distortion of time on the light that galaxies emit. So as I was saying, I think some minutes ago, the idea of Einstein is that we have distortions in space and time, and so we have gravitational potentials. And so if you take a galaxy, this galaxy will be sitting at the bottom of a gravitational potential. And so you will have this gravitational potential that is made of dark matter, and then the visible matter is more or less located at the bottom of it. So that's the idea.
Maybe you need to explain very briefly for people that don't have a background in physics, what is a gravitational potential?
So it's really this distortion in the fabric of space-time. So as I was saying, we can picture the universe as this immense tablecloth. And then if you take a massive object, then this massive object will create a deformation. And this deformation is what is called a gravitational potential. Well, that is a distortion both in space and in time. And so the idea is that if you have a galaxy that is sitting at the bottom of this gravitational potential, then the light that it emits will have to escape from the potential in order to reach an observer. And in doing so, this light, which we can picture as a wave, will sort of get stretched. It will lose energy and thus get stretched. And when we stretch the light, this means that we change its so-called wavelength or frequency. And this determines the color of the light. So the more we stretch the light, the redder the light will get. And this is actually a consequence of the distortion of time, because it's a consequence of the fact that time passes more slowly at the bottom of the well rather than outside of it. And this is why the frequency of the wave changes. And so we have this effect, this reddening of the light that is called gravitational redshift. And we can measure this gravitational redshift.
And we also observe this redshift due to the expansion of the universe, right?
Exactly, yes. So, but this is a crucial point actually, because this is not the only effect that changes the color of the light. There are many other effects actually. So there is the effect that is due to the fact that the universe is expanding in an accelerated way. So a given source of light, like a galaxy, will be receding with respect to us. It will be moving away. And so the light that it emits will also get stretched by the expansion of the universe. And this is one type of redshift. It's called cosmological redshift. Then on top of this, we also have a redshift that is called Doppler redshift, That is due to the fact that galaxies have peculiar motions. They have so-called peculiar velocities that are in their local environment. On top of the expansion of the universe, for example, I can have two galaxies that are moving towards each other because they are gravitationally attracted to each other. And so this will also change the redshift. They will also change the color of the light wave if this also has a component of velocity with respect to the observer. And then there is this third type of redshift, which is the gravitational redshift, the one that is a consequence of the distortion of time, that really comes from the fact that the light escapes from a gravitational potential. So while the other two types of redshift are due to the fact that galaxies move with respect to us, this third type, the one I'm interested in, is really due to gravity itself. It's really due to the fact that lights escape from a potential.
Wow.
So it's cool, right? It's very fascinating.
Yes.
And so the idea is that we can measure this effect. And so people have found ways of isolating this gravitational redshift effect from the other two types of redshift. And one can do this on different scales, actually. So if you go to relatively large scales, but not too large, like galaxy clusters, for example, then this effect has actually already been measured. It was measured in 2011 already. But if you go on very, very, very large scales, then measuring this effect requires more data. And so we haven't measured it yet on these very, very large scales. We need new data, more, let's say, data points, more galaxies. And so we will be able to perform this measurement on the largest scale possible actually in the coming years with new galaxy surveys that will map new galaxies, more galaxies. So we will be able to make this measurement also on these very, very large scales.
So here I have two questions. Let's start with the first question. Does it matter how you see this, the light particle, based on which side of the gravitational potential well you are on?
What really matters is really what is the difference in height that the light has to travel. That's really the only thing that matters. It doesn't matter what is the exact path of the light wave. What really matters is just the altitude difference. It's the same as if when you go on the mountains and you take a hike, then what really matters in terms of altitude gain, if you go down a mountain and then you go up again, then your altitude gain could be exactly zero. In this case, you will have no gravitational redshift. If you go down a mountain a little bit and then you go up by a lot, then you will have, you will have an altitude gain that is very large. And then this is what matters. This is the gravitational redshift.
I think that's a very fitting metaphor given the fact that we both live in Switzerland, where
Exactly.
hiking and climbing are very common hobbies.
Exactly.
In fact, yeah, actually, this makes a lot of more sense now. Thank you. And so we're talking about this expansion of light. Just as a general overview, I understand that this is not part of the PhD thesis, but as a general overview, what happens when light does the opposite? And instead of moving away from you, or instead of it losing energy, what happens to this light when it, in fact, it gains energy?
So this is a good question. So the idea is that if you have, so first of all, for the cosmological redshift, if you have a source that is moving, towards you, suppose that the universe was contracting, then the light would get more squeezed and it will change color but become more blue. And it's the same also for the gravitational redshift. In this case, you don't have an actual movement of the galaxy, contrary to the cosmological redshift and the Doppler redshift, where the galaxy moves with respect to you. In this case, with the gravitational redshift, you just have the fact that the light is going out of a potential or going inside a potential. So when the light loses energy to go out of a potential, it will get stretched and it will become more red. If the light goes into a potential, so it goes down, it acquires energy, and it will also become more squeezed, and so it will become more blue. It's the same idea. So if you stretch a wave, it becomes redder. If you squeeze it, it becomes more blue. And it's always the same. So the idea is that if you have a galaxy that instead is outside of a potential, and you have an observer that is at the bottom of a potential, then the light will have to sort of go inside the potential and it will acquire energy doing it, and it will appear more blue in some sense.
Yeah, actually, now the puzzle pieces are all coming together. I'm starting to see the big picture. And so, because we're coming towards the end of the episode, my question here for you is this. What did you conclude at the end of your PhD? You know, you did your research, you studied the distortion of time, and what was your conclusion? What's happening out there?
Exactly. So all of this that I've described to you is something that was, let's say, pre-existing to my PhD. So we knew that time was distorted. We knew that there was this gravitational redshift effect. But what we didn't know is how we can use this effect to test the properties of gravity. So I'll try to put all the puzzle pieces together. The idea is that since if you can measure this gravitational redshift, if you can measure this distortion of time, then you can measure how deep a gravitational potential is directly, because you can see how much you have stretched your light wave, for example, or how much you have squeezed it. So this is a direct measurement of the depth of a gravitational potential. Now, what you can do with this measurement is that you can combine it with a measurement of the velocity. You can look, for example, at how quickly galaxies move in a galaxy cluster, for example. And you can compare these two measurements in the sense that you know how deep your potential is, and you can check how quickly the galaxies move, and you can try to understand whether this motion of the galaxies would correspond to the same depth of the potential as the one that you have measured with gravitational redshift.
And what does this tell us if it's the same?
If it's the same, then it means that the equivalence principle holds. It means that we have understood how, let's say, that matter, the matter that is contained in the galaxies, and the light that climbs out of the gravitational potential experience gravity in the same way. If there is a mismatch between the two, then it means that the gravitational potential, let's say the depth of the potential that you measure from the gravitational redshift, is different from how the galaxies move. And so this means that there is something strange, there is something funny happening at the level of how the galaxies move. And so the depth of the potential that you would require for the galaxies to move in a certain way is different from the one that you measure by looking at light. And so this could tell you that, for example, there is something strange happening at the level of dark matter, the dark matter contained in galaxies. Because it could be that the dark matter that is contained in the galaxies experiences gravity in a different way from standard matter. And so going back to what we were saying some time ago, the equivalence principle, the one that Galileo was trying to test by throwing different objects from the Pisa Tower, may not hold for dark matter. And so if dark matter experiences gravity in a different way, maybe there is an additional force that acts on dark matter, then the motion of the galaxies will not be compatible with the depth of the gravitational potential that you measure from gravitational redshift. And so it could be that there is a breaking of the equivalence principle.
Wow.
I don't know, maybe this was a bit too technical, but
No, for sure. You really, no, this was not technical. Okay, and what does this tell us about the nature of dark matter?
So first of all, this is something that during my PhD, I demonstrated that we can do this. Now, I haven't doing this test actually requires more data. If you go on very, very large scales, as I mentioned before, we don't have measurements of this gravitational redshift yet. And so we haven't been able to perform this test because we have to wait for more data to be able to make this measurement. Whereas if you go to slightly smaller scales where gravitational redshift has already been measured from galaxy clusters, then performing this test is actually the next step of my work. So far, I've demonstrated that one can do this. We came out together with my supervisor and my group and my collaborators. We came out with this idea. We've shown with gravitational redshift, you can test whether the equivalence principle is valid for dark matter. And then applying this to the measurement of gravitational redshift that is already available in galaxy clusters, then it will be the next step of the project. So for example, I'm part of the Euclid collaboration, So the Euclid satellite is a satellite of the European Space Agency, which was launched a couple of years ago, and it's collecting data at the moment. And as part of the collaboration, I will be in charge of performing the measurement of gravitational redshift from galaxy clusters observed by Euclid. And starting from this, then we will be able to perform this test of the equivalence principle. And this is the next step of my project, of my research.
That's amazing. Like Galileo, you will stand at the top of the but of the universe and like try to drop the galaxies, the matter, everything, and just see if gravity affects them the same. That's this is a very abstract question, but do you think that let's in this for the case of this question, and we assume that in fact the story is true, when Galileo went up to the tower and he wanted to test gravity, do you think he thought that there was ever going to be a day where people test this exact same idea, but to galaxies in the universe?
Very hard to speculate, but Galileo was surely a person with a huge imagination, which is something that is definitely needed for a scientist. It's a very creative work, actually. And so I'm pretty sure that he was dreaming of, sending satellites in space already at the time. I guess he could not, maybe he could not suspect that there would be a form of dark matter, but I'm pretty sure that he would be happy to know that people still test this in different ways.
So is this what you're hoping to do for your postdoc position? Kind of, you had this idea along with your team, you checked it, you proved that in fact it is something that we can test, and now comes here, how do you say, testing time distortion part 2, actually doing the work that you proved you can do in part 1.
Exactly. So this is why what is very exciting is that there is all this new data coming. And so actually putting this test into practice will be extremely interesting. And so this is the objective indeed of my future work. So starting from this fall, I'll actually move to Germany, to Munich, to the Max Planck Institute for Astrophysics, to carry out a project about this. So to put this test into practice. And then there is a whole part of the project, which is also to try to understand how we can combine this method with other new observables, like the distortion of time, that we can also use to test fundamental properties of gravity and dark matter. So trying to understand how we can use other probes. For example, if there is something related to gravitational waves that one can use, or to use other ways to map the distribution of matter in the universe. Instead of galaxies, for example, we can use type 1a supernovae, which are a special type of stellar explosions. One could also use them to probe how matter is distributed across the cosmos. One could use gravitational waves, and one could also use other effects. I mean, people have already worked a lot on testing how gravity works through gravitational lensing, which is actually the fact that light rays get distorted by the presence of massive objects. So the path of photons get distorted. And so also including all this in my work will be very interesting. And so there are actually many ways, many tests that one can do using cosmological observables, and combining all of them will be very exciting for sure.
Yeah, very excited. In fact, thank you so much for sharing this research with us. It's honestly, you have left me speechless. This is very cool.
Well, thank you so much for the opportunity. And I wish to underline that this is also a very collaborative effort. There are so many people who have worked directly with me about this, and also so many people who are working on testing different aspects of gravity. So for sure, if you want to keep an eye on all of this, I'm sure that there will be interesting results coming, well, in general, from the Euclid collaboration and from other collaborations in the coming years. So it's really an international cooperation that is sort of driving us towards understanding more and more about the universe. And I think this is also the beauty of science, that it's very, very international. It goes across borders, something very important.
I actually say this in my little intro before every episode. I say a curious mind is a happy one. Because I think if we are as human beings all busy being curious and collaborating in the pursuit of science, in the pursuit of knowledge, then we forget about fighting with each other and and all the politics and all of this stuff, because we just come together for the pursuit of one common goal, and it's uncovering the secrets of the universe. And then just before we finish up, is there anything that you want to say to anybody who's listening, anybody who's passionate about cosmology, or somebody who's maybe intimidated to pursue a career in this? What kind of message do you want to send out into the world?
So actually something that I wrote in almost the very first page of my PhD thesis is a section called On the Value of Cosmology. So something that I've asked myself a lot throughout my PhD is, why is it valuable to do this in a world that, you know, faces so many issues and problems, and especially in this historical time, why should we devote time, energy, effort in order to trying to discover something about the cosmos? And I think my answer to this is that for sure it stems from our human curiosity. It's something that we've been doing since the dawn of time, probably, of us as a human species. It's really in our DNA. And I think being part of this quest is a privilege and an honor. And I would encourage any young person who's passionate about this to really dive into it, because there is so much to learn, and there is a lot of value in trying to understand, you know, the fundamental laws of nature. And as I was saying at the beginning, this also gives us perspective on our place in all of this. It puts, you know, our problems into perspective, and it makes us feel part of, you know,
Something bigger. Yes.
some larger cosmos that is inconceivably bigger than us. And I think there is a lot of value in this, and science needs more and more voices, more and more diverse voices, more young people, and more resources as well. Because I don't deny that it's a career, it's a path that requires sacrifice. It requires moving around, it requires effort. But if passion drives you, then I would encourage anyone to join this journey.
Wow. I think this is a very beautiful time to end the episode right here. I want to thank you so much again. Really, I feel like I need to do some standing ovation or something. Been wonderful. I can really truly see the passion that you have for this field, which, this is something that we share. And thank you for taking the time and the effort to really, take this research, which by no means is simple, but really simplifying it in a way for anyone to be able to understand, because this is what it seems like you're able to do.
Thank you so much for the opportunity. I'm really grateful to be able to be here and tell my story, my research, and share it. Thank you so much.